Swayam Prabha. Digital India. Educated India.
Good morning everyone, welcome back to the second lecture on the topic of displacement measurement. So, in the previous lecture we have learned about two of the different methods for displacement or stress measurement, namely the potentiometer and also the resistive strain gauges. Both of them have same working principle, that is, as the length of a conductor changes, the corresponding resistance also changes, but they are implied in a different way. Potentiometer generally is used for larger scale application, whereas strain gauge can be much smaller in size and therefore can directly be attached to the specimen where you want to have some kind of displacement or stress measurement, and we can get extremely small deflection also recorded in the device. So, today we shall be moving forward to learn about a few more such kind of devices, preferably electromechanical transducers, that is where the displacement is generally converted to some kind of electrical signal. Like the two we have discussed in the previous lecture, they are also electromechanical transducers, but today we shall be learning about 2-3 more electromechanical transducers and maybe 1 or 2 more which are not electromechanical but something else. Let us see, depending on the time, how we can go for it. But as we always keep on doing, we shall be starting with a little bit of exercise. And now this problem I mentioned in the previous class itself on potentiometer. So, I hope you have already tried to solve it. So, I shall not be giving a complete solution for this, just some rough idea about how to solve it, because I do not have all the calculated values for this one, but just to see if the way I am trying to solve this, whether it matches with your idea or not. So, what is given here? Here we are talking about a potentiometer which has a length of 8 meter. So, you have L equal to 8 meter and the resistance of the corresponding wire R is equal to 20 ohm. So, corresponding potential drop should be equal to, we are yet to get the voltage here, sorry. We are connecting this particular potentiometer with a cell of EMF 2 volt. So, we are talking about a voltage of 2 volt. Instead of using V, let us use something that we have done earlier. So, EX or VX. And there is something new, that this cell itself has an internal resistance of 2 ohm. So, we will be coming back to this later on, but before that the potential drop K should be equal to the excitation voltage divided by length. So, it is equal to 2 volt divided by 8 meter, this much of voltmeter, that is 0.25 volt per meter. This is the potential drop for this, but now they are saying that the potential drop, this is the potential for this. Now, they are saying that this potential drop has to be limited to 20 microvolt per millimeter. Actually, the calculation that we have shown here, that is wrong, because here we are not taking care of all the resistances. It is mentioned that we need to have this particular amount of potential drop. So, let us calculate in a different way, but before that, what is the configuration that we have? Here we have a cell and then we have the resistance. This is the resistance which is having a value of 20 ohm, but how the cell is looking like? The cell here has an internal resistance, that means in your circuit actually you have this cell of EMF 2 volt and then this is the internal resistance for this cell, this is the 2 volt and this is this 2 ohm internal resistance. This is also present in the circuit, and now we are adding another rheostat, that is, we are adding another rheostat to this circuit to complete this one. So, we are having a 2 ohm internal resistance, then a 20 ohm resistance for the resistor, and we have to identify this particular rheostat resistor or SH or let us say write RH, we have to identify its value so that we can get the total potential drop to be 20 microvolt per millimeter. Now, we know that this K is equal to X by L. Now, whatever the, if we write this in terms of the current that is flowing through, generally we write it as IR upon L. Now, how much is I? Here it will not be equal to X, it will be equal to the voltage drop that is we are having across this, that is if this is VO. So, this will be actually this VO by L. Now, it is IR by L. Then now how much is I? Look at the circuit. If we erase this one now, in your circuit your I should be equal to the cell EMF that you are providing by summation of all the resistances. So, I is replaced by X into R by L, and summation of all the resistances. How many resistances we have? We have a 20 ohm resistance for the resistor plus 2 ohm internal resistance plus this RH. This thing should be equal to that 20 microvolt per millimeter, or if we can write in terms of SI in it, 20 into 10 to the power minus 3 volt per meter. So, from this the value of Ex is given to be equal to 2 volt, capital R is given to be 20 ohm. From there you can easily identify the value of this RRH. So, this is the procedure that you have to follow here. Be careful that here we are talking about not one but 3 resistances. One corresponding to the resistor itself, for the potentiometer, one the internal resistance of 2 ohm corresponding to that cell EMF, and also the rheostat which we are adding this in the circuit to modify the potential drop. Let us now try to solve something for the strain gauge, the resistive strain gauge that we have learned in the previous class. Let us try to solve a problem on that. So, a quite straightforward problem is given here. For the strain gauge, we are having a resistance of 120 ohm, then it is mounted on a specimen, and the specimen is having an Young's modulus of 200 gigapascal. Now, there is an axial loading has been applied on this. Here we are assuming that the strain gauge is also mounted on the axial direction only, so that it can directly sense this particular loading. Now, the length of the rod has changed by 3%. Now, what does this mean by, what is this 3%? This is basically this delta L upon L to be equal to 3% or 0.03, and the resistivity of the material changes by 0.3%. That means delta rho upon rho is equal to 0.003, and it is also given that the Poisson's ratio is equal to 0.3. So, now how can we calculate the gauge factor? What is the definition of gauge factor? Gauge factor, commonly represented by SG or some similar symbol, is delta R upon R divided by delta L upon L. Now, delta L upon L, which can also be related to the strain, that is directly given, and R is also given, but delta R is the one that we have to calculate. How can we calculate delta R? You remember the derivation that we did in a previous class. So, delta R upon R can be related to 3 factors. What are the 3 factors? It was 1 upon 2 nu into delta L upon L plus delta rho upon rho. Do you remember the derivation for this, how we calculated this? There are 3 components, and the first part is related to the change in the resistance because of the change in length. This is because of the change in cross section area, this is because of the change in the resistivity. So, you have all the values available. So, you put there 1 plus 2 into 0.3 into delta L upon L is given as 0.03 plus change in resistivity is equal to this, leading to, I have calculated the numbers for you, it is equal to 0.051. So, your SG is equal to 0.051 divided by 0.03, which leads to 1.7. So, this is the first answer. We have the gauge factor. And now we have something very interesting. It is given that the connected device, here with the strain gauge we are connecting some device to identify the strain change in resistance, something like a Wheatstone bridge, and the device itself measures this change in resistance with an accuracy of 0.02 ohm. So, we have to identify the uncertainty that is involved in the final stress and strain measurement. which is actually getting induced because of this uncertainty in resistance estimation. How can we estimate this? Let us first start with the stress. So, how we can get stress? We know that the Young's modulus is defined as stress upon strain, or stress is equal to epsilon into E. Now, how much is epsilon? Epsilon is delta L upon L, but we can write in a different way. We know that Sg is equal to delta R upon R divided by epsilon. So, from there we can write epsilon is equal to delta R upon R into Sg. Why we are getting this delta R into equation? Because delta R is actually the one that refers to the change in resistance, and so its uncertainty will be involved there. Now, if we get that here, so we have delta R to E by R into Sg. This entire bracketed term if we take as constant, because E is generally a property of the material that is given, gauge factor can be taken as constant, and R is the resistance of the strain gauge, initial resistance, which we do not have any information about the uncertainty involved there. So, we are also taking that to be a constant. Then if we differentiate, del sigma delta R will be how much? Will be E by R into Sg. That means the uncertainty involved in this estimation will be equal to sigma del delta R into the uncertainty involved in delta R, that is equal to E by R Sg into the uncertainty involved in delta R estimation. Now, we have, or we should put a plus minus symbol before this, because uncertainty can be plus or minus. So, if we put the values, your E is given as 200 GPa, that is 200 into 10 to the power 9. Always try to convert everything to SI units. So, it goes to Pascal. R is given as 120 ohm, Sg we have just calculated as 1.7, and uncertainty is 0.02. It is given in absolute unit only, so there is no need to convert anything. So, corresponding uncertainty will come to be plus minus 19.6 megapascal. This is the uncertainty involved in the stress estimation. And how much uncertainty is involved in the strain estimation? Now, we can directly make use of this particular relation from there. So, this will become 1 by E into uncertainty involved in stress estimation, that is this plus this plus minus 19.6 divided by how much was E, that was 200 into 10 to the power 9, 10 to the power 9. Be careful, the numerator there has to be a 10 to the power 6 also, because that is in megapascal. So, once we put the values, it comes out to be, actually I have not calculated the values, but we can easily calculate it from here. So, it is 19.6 divided by 2 into 10 to the power minus 5, and if we calculate from there, so it becomes 9.8 into 10 to the power minus 5. This is the uncertainty that is involved in the strain calculation. So, this way we can connect this one to something that we have learned actually in chapter number 1. Remember how we did that, the uncertainty analysis there. This is precisely the procedure. Once we have the relation here, E, R and Sg are taken as constant. So, delta R is the independent variable and sigma, the stress, is the dependent variable. So, we calculate this formula, and this is the one that we have derived there. So, making use of that, rest is quite straightforward. So, this way we can also estimate the uncertainty involved in any kind of strain gauge measurement just from the simple knowledge of the accuracy of the corresponding Wheatstone bridge or whatever instrument you are using for measuring the change in resistance. That completes our discussion on the topic of resistive based instruments. Just one small thing that I would like to add. I do not have too much space available, let me make a small space somewhere here. We have seen there the ratio Rp upon Rm should be very small, or should be very small. That is when Rp is very small, then only we can neglect that loading effect and we can get a linear representation of quite accurate 0th order representation. So, RP should be very small. On the contrary, RP should be large in order to have a high resolution. That is another way actually we can, without increasing the value of RP, you may think that we can also increase the value of the excitation voltage, because what was our relation? Our relation was E out by, let me write once more here, our relation was E out by E x is equal to x I upon x t. So, if we increase this E x, then also we can get a higher resolution, higher the value of E x, the resolution will be more, but practically that is also not possible, because we also have to take care of the total power that a potentiometer is dissipating, and that is generally fixed. Most of the potential that you get, they generally come with a power rating 5 watt, 10 watt or something like this. That means whatever power it is going to dissipate, the voltage has to adjust accordingly. Now, what is the, or rather the excitation voltage has to get adjusted accordingly, and also the value of resistance. Now, what is the relation? We know if P represents power, that will be equal to x square by R, that is the voltage that you can put in, that should be equal to root over P into R, where P is given, or I should say RP. So, here this P is the power that is generally specified, we generally can't go to very high power level, therefore, whatever may be the value of RP, Ex has to be adjusted accordingly, and we can't just put any high value of Ex. Yes. So, that completes our discussion on potentiometer and resistive strain gauges. Let us move to a different category of device. The next device that we have in line are inductive devices. Like in the previous case, we made use of the change in resistance to measure displacement. Here we are going to make use of the change in inductance in some coil, inductive coil, to measure the displacement. And the device that we are going to talk about here is known as LVDT, or linear variable differential transformer, an extremely common method of displacement measurement, can operate a very wide range of parameters or wide range of distance values, and is a very common measurement device in some very critical application areas. So, as I mentioned here, the concept is the change in inductance of a sensor coil on displacement leading to the change in the current or voltage across the coil. So, here the arrangement is something like this. The simple design of LVDT involves one permeable core, and one side of the core we have a single primary winding. It is quite similar to a transformer. Only difference is that here instead of one we have two secondary windings. So, the core, when they are in their normal position, the core is located at the center position, or I should say the primary winding is located at the center position, and both the secondary windings are equally placed with respect to the primary. Therefore, same amount of mutual inductance will be induced in both of them. Now, the core is the one that is connected to a displacement sensor. So, whenever there is some kind of displacement, the core itself will move, thereby changing the relative position of the primary and secondary, and accordingly the inductance or mutual inductance in the secondary coils, their magnitude will change. Under normal condition, like what we can see here, let us say if we plot with respect to time, then if the primary is subjected to a sinusoidal voltage like this, both the secondary coils will also exactly follow the same. My drawing shows some kind of phase lag here, but actually that is not there. Both of them will follow it exactly. However, whenever there is some kind of deflection, then there will be some kind of phase lag induced in them, and the voltage values will not be same in both the secondary windings, thereby leading to some output voltage value, which with proper design can be made directly proportional to the displacement of the core. So, under normal situation we have this ES1 to be equal to ES2 when the core is in its normal position, or sometimes referred to as a null position, because we get this ES1 minus ES2 is equal to 0 in that situation. However, when the core is moved because of the displacement, some displacement, then ES1 minus ES2, that will not be equal to 0. So, that will give some kind of output voltage, and that output voltage will be directly proportional to this displacement of the core. That is the operating principle of LVDT or generally any kind of inductive devices. So, this is a typical configuration. What we have here, we have the core. The core is generally made of highly permeable material, something like nickel iron material, and there will be a threaded hole through this center of the core. So, the on core we have on one side we have the primary winding, this is the primary winding, and these are the two secondary windings. They are encapsulated inside a particular medium, and generally both ends of this one, this end and this end, they are open, so that in extreme situation, if it is subjected to some kind of displacement value which is beyond its limit, the core will just move outside the shell, thereby preventing any kind of damage. So, this is the simple construction of an LVDT transformer. It offers a huge amount of advantages compared to the other displacement measuring device. The first big advantage is friction free operation. Here there is no direct mechanical contact between different components. The primary winding, the secondary winding and the core all are separated from each other, and therefore, they can move without any kind of rubbing effect. They can give very large operating range. The range of such kind of device operation can be extremely large, ranging from a few microns to about 500 millimeter, and in certain special design cases it can also go up to even the value of 1 meter. Next is infinite resolution. Now, the resolution of the device in a way theoretically is infinite, because even with the smallest possible displacement there will be some kind of output voltage produced, and therefore, its resolution is infinite. I hope you remember how we define resolution. It is the change in output corresponding to the change in input, or you can say resolution mathematically is change in output divided by change in input. Now, whatever may be the smallest possible change in input that you can think about, there will be a change in the output, that thereby giving the infinite resolution of the device. But practical cases, the resolution will be finite, because there can be two things. One, there can be some kind of noise incorporated by the signal conditioning apparatus if there is any, and secondly, which is much more relevant, that is the voltage, output voltage, that of course we have to measure by using some kind of voltage measuring instrument like a voltmeter. Now, that may have certain kind of resolution, and that is why mostly the resolution of the LVDT depends on the resolution of this voltage measuring device. Next, extremely long mechanical life. As we have mentioned earlier, there is no friction, so there is no direct wear and tear, there is hardly any aging effect, and we can have very long life. Very long means refer to really very long, something in the range of 150-200 years that we are talking about. Over travel damage resistance. As I have mentioned here, both ends are open to this, and therefore, if the core is made to travel more than it is supposed to, no damage will be done. It can be protected, and also as the core pops out of the system, there will be of course no voltage induction, no induction, and hence the device will stop working for that instant, and then you can easily get the core back into its normal position and device will be back. Now, single axis sensitivity, generally the core moves only in one particular direction, thereby sensing displacement only along that direction. It is often immune to any kind of transverse motion or vibration. The core and coils can easily be separated if required, like suppose if we want the core to move in some highly pressurized fluid, then we can easily separate the coils from the core by using some non-magnetic material, non-magnetic shell or tube, so that the pressurized fluid and the core remains inside that non-magnetic tube and the windings remain outside there, thereby easily protecting the windings from this high pressure. Environmentally they are robust, even in flammable or corrosive environments also we can use this, or like I just mentioned, if we are working with a high pressure flow field, there also they can easily be operated with. Null point repeatability is the null position of the null is very important, because when it is not subject to any kind of displacement, then we should get a zero voltage, which we refer to as this null point or null position. Now, the null position is highly repeatable even after several fluctuations, even when the instrument is subjected to some fluctuation measurement, repeatedly changing the position and then going back to null, it is able to reproduce a null quite regularly with high accuracy. and also it doesn't suffer too much because of the changing the operating temperatures. The null position generally is retained even at very high temperatures. The dynamic response is very fast. It is limited only by the mass of the core itself, and that mass generally is very small. So we get quite fast response. Again, the response that actually we will be getting, that depends on the resolution and the response of the voltage measuring instrument. And finally, we are talking about absolute output here. Even if there is a loss in power during the operation, whatever last position the core was, it will remain in that position, and as soon as the power is back, it will start to operate back again. So we always get an absolute output from this particular device. So these are some of the advantages. Very important of this particular list, we can think about this friction free operation. We have this large operating range, infinite resolution, and this long mechanical life. These are all very important points, and of course we also have to talk about the robustness of the device. Yes. And because of so many advantages and also the high accuracy that they are able to provide with such large level of resolution, then we can easily use LVDT in all possible kinds of application, starting from simple laboratory experiments for measuring the displacement of, say, a tool post on a lathe, to something related to the space travel or satellites. However, in most commonly we do not use the voltages that way, do not use the secondary windings that way. Rather, what we do is referred to as the series opposed secondary. The series opposing secondary refers to this. Just look at this diagram here. The opposite ends of the two secondary coils are connected with each other. Thereby, your reference voltage V1 and V2 will, the output voltage V1 and V2 will always be opposite to each other, thereby giving V naught equal to V1 minus V2. So this is what we refer as a series opposed secondary. This is generally the most popular configuration for LVDTs. This is how they operate. Like when the core is at the null position, just look at this first, then both coils will be having same voltage induced, and so you will be having E out equal to 0. When it moves towards the left side, the core is moving towards left, then the mutual inductance in S1 will be larger than that induced in S2, thereby E1 will be higher than E2, and you will be getting a net value of E1 minus E2. Similarly, when it moves towards right, the mutual inductance in S2 will be more compared to S1, so E2 will be higher than E1, and you get E2 minus E1. Therefore, not only the magnitude, you also get a sense of the direction, on which direction the core is moving, or in a way your sensor is moving. The series opposed secondary configuration is the one that is the most popular one. Let us now, but this is the situation that we are talking about when the output scales, or I should say the output nodes are open, means we are talking about an open circuit voltage. However, practically we have to connect some voltage measuring instrument there, thereby giving some kind of loading effect, and we have to get an idea about the loading effect. So let us try to do that with some simple mathematics. So initially we took the configuration something like this. So this is your primary. Let us say, okay, instead of drawing this way, let us draw this way. So this is your primary side source, the resistance of the primary circuit, and the inductance of the primary circuit. So this resistance, let us say R primary, this is L primary, and this is your source, say E excitation. So a current IP will be flowing through this. This is the core, and now you have two secondary coils. This is the first secondary coil and its corresponding resistance, and then we have the we should have drawn the secondary voltage as well. So this is the secondary side voltage, and similarly on the other coil also we shall be getting something there. This is the series opposed configuration. So when this side is open, then we are going to get some voltage, say E naught here between these two. Let us say the total resistance of the secondary is divided equally into the two circuit. Similarly, the inductance also is divided into 2 as Ls by 2, and we get ES1 here and we are getting ES2 here. So, when the circuit is open, then if we apply Kirchhoff's law on the primary side, then what we are getting, there is a current IP flowing through the resistor RP and also this inductor LP, then we can write RP IP plus LP dIP dt minus EX is equal to 0. So, this is for the primary side. This primary current which is flowing through this coil LP, that will induce something on the secondary side voltage. However, the secondary being open circuit, there will be no current flowing through the secondary side. Now, how much will be the mutual inductance? If M1 refers to the mutual inductance in coil number 1, then I should say ES1 will be equal to M1 into dIP dt. Similarly, the voltage induced in the secondary circuit ES2 will be equal to M2 into dIP dt, where M1 and M2 refers to the corresponding mutual inductance. M1 is the mutual inductance in coil 1, secondary coil 1, M2 is the mutual inductance in secondary coil 2. So, the net secondary voltage E naught will be equal to ES1 minus ES2, that is M1 minus M2 into dIP dt. However, there is no current flowing through the secondary circuit side and therefore, there will be no inductance back on the primary circuit corresponding to this, and also no drop in the resistor. But this is the output voltage that you are getting. So, if we want to write a relationship between output and input, then we can write this way. Let us use our earlier notation. We can write this as RP plus LP to D IP to be equal to EX. That means, where D is the operator that we have used earlier, EX divided by RP plus LPD. So, if we take it there, we have now E naught is equal to M1 minus M2 into D of IP, that is, if we write D of IP, then what we have? We have D by RP plus LPD to EX, that is, we have E naught upon EX, it should not be EX, it is EX as per our notation. So, this is equal to again M1 minus M2 to D by RP plus LPD, and quite often we divide both numerator and denominator by with RP to get M1 minus M2 upon RP to D divided by 1 plus LP upon RP to D. What kind of system is this? This is a first order system, and in first order system, how we characterize a first order system? In terms of gain, static gain, and more importantly a time constant. Now, what is your time constant? Here this LP upon RP is the one which is your time constant. So, you can write this as 1 plus tau D, when with tau being LP upon RP. So, the value of the resistance and the inductance in the primary circuit determines the time constant for this particular situation when output voltage is not given, or rather output is open circuit. We can easily perform a frequency response because it is subjected to a periodic input. So, we can always subject this one to a periodic input like a sinusoidal wave, and then we can get a solution. I am not going to go for the detailed derivation because such kind of derivations we already know how to get the from our discussion on the second chapter, but from this you can easily calculate the form of E naught by EX into a form like this, where we have M1 minus M2 by RP into omega divided by root over 1 plus omega tau whole square to angle of phi, where omega refers to frequency and phi is the corresponding phase lag. And what will be phi? It will be 90 degree minus tan inverse omega tau. This calculation we have done earlier, you know how to calculate this. Not very important for I should say it is not mandatory for you to go for this derivation, rather up to this is sufficient. Yes. But now instead of keeping the circuit open, we are closing this by a voltage measuring device. So, we are connecting some Rm through this, where Rm refers to the resistance of the meter. Now, whenever we are connected, we have closed this circuit, then a current will be starting to flow through this. Let us say Is is the current that starts to flow through this, and as the Is is current flows through this entire circuit, then that will also put some inductance back to the primary side. That I mean, because of the presence of this current Is, the secondary side will be now inducing something on the primary side. So, we have to rewrite both the equations. If you rewrite the equation for the primary side, what we have? So, we have RP IP as usual, plus we have LP dip dt as usual, minus M1 minus M2 d Is dt minus Ex is equal to 0. This is the equation for the primary applying Kirchhoff's law, where this particular term is coming because of the mutual inductance by coil 1 and 2. M1 is the inductance imposed by coil 1, M2 is the inductance imposed by coil 2, and Is is the current that is flowing through both the coils. Similarly, for the secondary side, if we write now, for the secondary side M1 minus M2 dip dt is the current that has been induced into this, plus total resistance is Rs by 2 for coil 1, Rs by 2 for coil 2, and Rm is the resistance for the meter into I, plus total inductance of both the coils Ls by 2 and Ls by 2, that will be equal to 0. So, we can convert both of them into common equation, like the there are two equations. So, if we write in our preferable form, then we have for the first, from the first equation we have Rp plus Lp into d Ip minus M1 minus M2 into d Is is equal to Ex, that is from the first equation, and from the second equation if we write, here it should be Is. So, from the second equation if we write, it is M1 minus M2 d of Ip plus Rs plus Rm plus Ls d of Is is equal to 0. So, you have two equations and you can solve this to get the expressions for Is and Ip, and from there you can get the expression for E naught upon Ex, its entire nature you can identify from there. So, this is the mathematical part for an LVDT transformer. We can easily, if anyone is interested to know the frequency response, you can easily calculate from these equations. Here interesting to know that as the equations are given, we can the phase difference or the output voltage and phase difference both will strongly depend upon the frequency of the input signal, and with the frequency that will keep on varying, both phase lag and this. Therefore, the system will provide accurate performance for only a certain situation. Now, we move to the next device that is also inductive in nature, and its operating principle is somewhat similar to LVDT, but with a difference. Here instead of two, we are having just one secondary side. There is a primary side and there is a single secondary side, but they are not like normal coils, rather they are given some special shapes. The induction, and also while LVDT is mostly used for linear displacement measurement, this inductocene can also be used for rotary displacement measurement. Rather, they are more commonly used for rotary displacement measurement only. Now, the induction patterns that we are generally dealing with in inductocene, they are given rectangular forms. In any inductocene, we generally have two parts, one stationary part and one moving part. If you are talking about a linear differential transformer, then the stationary part is known as scale, moving part is called slider. Stationary for linear displacement we call them scale and the moving part is slider, whereas for rotary case more conventional terminology is stator and rotor. Stator the stationary one, rotor is the moving one. Now, both stator and rotor or slider and scale, they are given the form of rectangular forms which are printed on certain surfaces. When current is fed to the stator side or the slider side, the voltage is energized to scale on the slider or stator side. I think I have made a mistake while writing this. On the slider or rotor side, this should be rotor side, the moving part, where alternating current is fed, the voltage is energized to the scale pattern due to the inductive coupling action, and the energized voltage will vary as the relative position of the stator and rotor that keeps on changing. You will get more idea from this structure that we are trying to say. So, this is the initial position, the position A refers to the initial position. Look at this, we have a repetitive rectangular pattern, a pattern something like this for both the scale and slider. The scale is a very long structure, slider is a much smaller one which has the same nature, but much smaller in total length, and initially they are perfect, the slider is positioned perfectly over the scale. Now, if you can see, the direction of flow of current are parallel, the same, and they are parallel to each other, and because of this the degree of electromagnetic coupling is the highest at this particular position. So, giving a very high output voltage value. Now, because of the displacement of whatever specimen that we are using for, if there is 1/4 pitch movement of the slider, then now in this case the direction of current flow in the scale will be negated by the direction of the same in the slider, thereby giving 0 electromagnetic coupling. With further movement, when it moves half pitch, then they are moving again in the same direction, but actually overall direction of flow of current is opposite between stator and rotor or slider and scale. So, it becomes coupling becomes maximum in a negative direction. For further 3/4 pitch displacement or further 1/4 pitch displacement, giving a total displacement of 3/4 pitch, we are back to 0, and finally when the movement is full 1 pitch, then we are back to again to the final value or the whatever we started with, that the maximum degree of coupling. So, the degree of electromagnetic coupling between stator and rotor or slider and scale, that depends upon their relative position, and as the position keeps on changing, the coupling also changes, and the corresponding output voltage that can directly be related to the displacement, generally using a linear relationship. So, inductocenes are very accurate device, again quite easily operatable and quite easily be understandable for about the working principle. Sometimes instead of one, we can use two different patterns like this. Look at the positions, they are generally 1/4 pitch apart, and because of this, while we get sinusoidal response from one, we get a cosine response from the other, thereby covering both kinds of possibilities. Inductocenes gives quite high accuracy in the level of just 1 or 2 microns, or if we are looking for rotary displacement, it can be as small as 2 arc seconds. We get very high resolution of the level of plus minus 0.01 micron and also very high speed. Look at the resolution in case of rotary scale, we are talking about 10 to the power minus 5 degrees. So, extremely small resolution we can get from this. Direct detection, a scale mounted on the moving element, so directly we can get the value of the displacement. Environmentally they are robust, hardly unaffected generally by the presence of dust in the surrounding air, any kind of oily or oily or moisture particles present there, and they are generally very small in size. Thickness of an inductocene can be hardly in the range of 15 to 20 millimeter, therefore, the mounting space required for them is also much smaller compared to an LVDT. Finally, their mechanical life is also very long. quite similar to LVDTs. There is also no direct mechanical contact, the coupling is only by electromagnetic forces, and therefore they are not subjected to any kind of wear and tear, and they can have very long mechanical life, something in the range of again 200 years. So, finally, it is an absolute feedback system. So, these two are inductive devices. Now, quickly we shall be talking about one capacitive device, which is also called capacitance pickups, where we use the idea of capacitance to measure the displacement. The concept is quite similar to the previous two cases. Instead of resistance or inductance, here the capacitance changes because of the change in the dimension of the capacitor. Now, theory of capacitor is all known to you. When two conductive plates are placed very close to each other, the distance then we can have a capacitance something like this, where A refers to the area and D refers to the distance. The distance generally, distance between the plates, the distance generally can be very small or hardly in the range of 0.01 millimeter. Now, the capacitance can be changed in different possible ways. Like in this mathematical relation involve three terms, we can by to measure the displacement, we can change any one of them. Like if we are looking to measure very small displacement, then we can talk about the change in the value of d. Of course, the d should be very small. So, if you are looking for very small displacement measurement, the distance between the plates can be changed, and the pickups will be done in this particular direction as shown here in this A. Whereas, if you are looking for much larger displacement measurement, then the area will be modified. So, in the first case, you can see as the displacement is changing, your modified value of capacity C prime will be equal to epsilon A by d plus some delta d. So, it is actually a nonlinear relationship because capacitance changes with distance in inverse proportion. Whereas, when we are talking about a change in area, then C prime is equal to epsilon into A minus delta A divided by d. So, it is a linear relationship. Similarly, we can also change the position of the dielectric medium itself. So, thereby changing the value of epsilon, it is also somewhat like a linear relationship. So, that is also possible. It is less applied compared to the area related thing because their effect is quite similar, but the basic idea is when you are looking for very small displacement measurement, we look for a change in the value of d, the distance between plates, whereas when you are looking for much larger displacement measurement, we go for either change in the area or change in the position of this dielectric medium. Capacitance pickups can also give very high accuracy of the level of 0.01%. They have a large operating range starting from 100 microns to something in the range of several millimeters, and they can have very long mechanical life because the wear and tear is negligible. Of course, wear and tear is more compared to the inductocines or LVDTs, but still that is also sufficiently long mechanical life that we can get from this. And finally, they can be environmentally very robust just like the inductive devices. So, these are the different kinds of electromechanical transducers that we get, where we directly change any kind of electrical properties, either resistance or inductance or capacitance, and try to relate that to displacement. Let us quickly talk about one or two more transducers where we are not trying to change any kind of electrical property, but still we are getting an electrical property as output. Example can be the optical devices. Optical devices are very common for measurement of several kinds of parameters: pressure, temperature, flow, and displacement and motion are also no exception. The idea particularly with there are several kind of optical devices. Here we are talking about the fiber optic displacement sensors. Here the idea is very simple. Firstly, we have an optical source which can be a laser or LED. There are two optical fibers. So, the light that is produced by this laser source, that goes through this emitting fiber, and once it strikes the specimen wherever we want to do some kind of measurement, there is a change. Any optical device depends on the modification of some of the optical properties of this particular light beam. So, now this light beam after reflection will be coming back through the receiving fiber and will be detected by this photo detector. Depending on whatever phenomenon that is going on here between the emitted and reflected lights, so there will be some change in some of the optical properties. There are generally 5 optical properties which are more common: the intensity, phase, wavelength, polarization or spectral distribution. Different devices make use of different properties, but intensity and wavelength generally are the most common one. Depending on the nature of the phenomenon, the property will get modified, and that can be related to the concerned parameter which we are trying to measure, like the displacement in the present case. So, they are electromagnetically immune optical sensors. There is no there can be complete electrical isolation, lightweight and compact, they are extremely accurate, and one big advantage, we can have both point and distributed design. LVDTs, inductocines, strain gauges, they all require certain kind of areas. So, they are not suitable for point measurement, but here in optical devices we are talking about one light beam which can be as thin as a point, and therefore, we can easily go for a point measurement as well as we can have distributed measurement, and they can give wide dynamic range. Also, we can easily go for a multiplexing with the optical devices. So, their optical devices, because of all these advantages, are very popular in any kind of measurement systems. Generally, in all optical sensors can be classified into 2 categories. One is the extrinsic optical sensor, where the light actually goes out of your feed fiber, then some changes take place, and then only it return to the second fiber. That is, this is the zone where the light is actually outside your device. The other, intrinsic, where the light never goes outside, rather during its passage through the device itself there is some modification in its properties. So, this second one is intrinsic. Extrinsic one generally has a lower sensitivity and leads to connection problems, but they are very easy to use. We can easily go for multiplexing and they are cheaper, whereas intrinsic devices have much higher sensitivity and much lesser connection problem, because you do not have to get the light back into the second one, the light always remains inside your device itself. But they are tougher to multiplex, they need expertise for operation, and they are much costlier compared to the extrinsic versions. So, the intrinsic versions are generally used for measurements of rotational motion, acceleration, strain, vibrations, etc., whereas extrinsic optical sensors are used in temperature, pressure or liquid level measurement, flow measurement. We shall be seeing this application in the concerned modules. Now, for displacement measurement, this is a simple picture of the possible way we can do it. The lamp is produces certain light. As the light pass through your device, and say this is a specimen where you want to measure the displacement or you want to sense the position of this, then the light strikes the surface and reflects back, and this reflected light is sensed by the photodetector. Now, as the gap changes, the property of the reflected beam, that also keeps on changing accordingly. Generally, we get a relation of output voltage to this gap in this way. This photodetector actually converts the difference between the supplied light and the reflected light to certain kind of electrical signal, again generally preferably voltages in the range of millivolts. So, that output voltage with the gap shows this kind of nature. We can have one front slope operating regime in this, or we can have a back slope operating region where we have high target reflectance. Depending on the reflectance of the target, we can operate either on the front slope or in the back slope. The optical fiber can have a cross section view like this. There are different possible scenarios, like here these white ones are the one through which light is supplied, whereas the red ones are the ones which are receiving. So, this is a quite random one. This one here you can see all the receptors are located at the center, whereas in this case all the receptors are located at the periphery. This is a more hemispherical kind of thing, half is supplying, half is reflecting. This way there are several other designs of optical fibers are also possible, but the principle of optical detection of any parameter remains quite similar. Just what we have discussed here for displacement, we shall be seeing much more about this optical thing in later works, maybe in particularly in the chapter of flow. One final topic for today's discussion, that is ultrasonic displacement sensor. This is something probably you have heard about this. Just think about the echo, like when you stand at somewhere maybe close to a valley and there is a hill far away from you, if you shout something, then it echoes back. Now, how much time it requires for the echo to come back depends upon the distance from you and the hill or the sound reflector. That is precisely what we do in any kind of sonic based instrument, sonic based displacement sensor. Here the ultrasonic sensor produces a signal which goes to the object which we want to locate, and then it comes back. The time required for this signal to start from this point and then come back at this point is a measure of the distance from the sensor to the object. They have very high sensitivity. This particular principle is used in several vehicle based applications, like in ships to identify the position of the sea bed or ocean bed. They easily use this kind of sensor. The signal is supplied, the signal gets reflected, signal goes down through the water, gets reflected at the ocean bed and then comes back. From there they can easily sense how much is the depth of the water there. They have again very high sensitivity and they have high digital resolution. Here actually one thing you can see, as soon as the signal is produced from here, then the sensor will stop till it is detected back. Only when it is detected back, then only you can supply another one. So, it is quite suitable for digitalization, because we can have a certain gap. It is not for continuous operation, rather it is intermittent operation only, and we can have very high digitalization of the order of 16 bits that we are talking about. Their operating range can be high. Actually I have written here 3 meter, but it can be much more than that, like estimation of the depth of ocean bed, and they have high repeatability as well. So, that takes us to the end of today's discussion. Today we have discussed about 4 different kinds of instruments. First is the inductance based measurement, where the inductance of a coil changes with displacement, and there we have particularly talked about LVDT and a bit about inductocene. Then we have talked about 3 other devices very quickly. One is capacitive based sensors or capacitance pickups, where the capacitance changes depending on the displacement. Then we have talked about the optical displacement sensors very briefly, and also the ultrasonic displacement sensor. So, that is it for the day. In the next lecture we shall be discussing about couple more displacement sensors, and we shall specifically be focusing a bit on rotary displacement or angular displacement sensors. So, please wait till that moment. Thanks for your attention today.